Hello guys, we'll be starting in 5 minutes. So let's hope for someone to join. Okay. Okay, guys. So let's start today's session. So myself, Karan Tiwari, and I am a PhD student working in the Representation Learning Lab at Indian Institute of Science. Today we'll be covering the concepts of feedforward neural network, backpropagation, entropy, and information loss. So this was the content which was covered this week, and I hope that everyone is means okay with the content what was covered in the previous weeks, week 0, week 1, and week 2. Now in the third week, I will be firstly going through some of the concepts which was taught this week. Then we'll be solving the problems of last year assignment problems. Okay. So last year quiz problems we'll be solving it. So it will be helping you to solve the quiz problems on your own. So the main purpose of having this session is to get your doubts clarified and to revise the concepts which you means might have messed up. Okay, so I guess let's start. So let's start the session. Okay. So first of all, this week, fit for network, backpropagation, entropy, and information loss was covered. Okay. So what is the feed forward neural network? Okay. So as we know, our input belongs to certain dimension. Okay. So a data set is of this type. We are given an input and the corresponding output. Okay. And it's a tuple. With each input, we are given an output. Okay. And we are given certain number of samples, which we can use for training a neural network. Okay. So the dimension of X is D dimension, which I'm assuming, and Y belongs to R D prime. Okay. So the thing is, in the normal neural network, how does it looks like the means this Feedforward neural network? Okay, so neural network is just a sequence of matrix multiplication and a nonlinearity. So what do I mean by that? So firstly, our input belongs to certain dimension. Okay, we need to perform a sequence of operation which can convert it into an output dimension, which we can interpret as the model predictions. Okay. Now, what is the sequence of operations? Okay. So in the previous weeks, we were making a sigmoid neuron. Okay. We proved its universal approximation using a sigmoid neuron. That is, if we have a certain any function, 1D function I'm taking, for example, I can divide into bunch of rectangles. Okay. And approximation. So the thing is, if we have an input, we were multiplying it by certain weights. Okay. Then adding certain bias. Then we were applying a non-linearity to it. Again, multiplying it by certain weights, adding bias, and again non-activation. So like this sequence can go on. So this whole sequence representation is what is known as weight for forward neural network. Okay, so there is an interpretation of what is happening. Okay, so we are given inputs. Okay, there are hidden layers. This whole sequence is a hidden representation. Hidden representation, which is latent, means we are in the certain, we are performing some operation, that is a matrix multiplication. So matrix multiplication, what can it does basically? Either it can decrease the dimension, it can increase the dimension, or it can mutate our vector, it can enlarge our vector, it can decrease the vector size. So these are the operations which matrix can do when operated on a vector. Okay, so we have a hidden representation in which each input is connected to the all the hidden representation. Okay, we can have more hidden layers. Okay, and finally we need to project it to the dimension of the output, because that is what we want. We want our model to give a prediction. Okay, guys. So this was our input. This is our output. Okay. Each neuron composed of summation of W layer xi in the previous layer, where I from 1 to D, plus bi, certain bias, B, which is here. So basically what is happening is some bias term is also getting added. Okay. So this whole network, this connections is just a matrix multiplication, as simple as it is. So suppose this is my X, this is my H1, this is H2, this is Y. So H1 is just a non-linearity, which can be a sigmoid, or in the neural network, the most commonly used is value. So it's a function which is zero if my input threshold is, if my input is below zero. Afterward, it's the same value. Mathematically, it can be written as f of x, where f of x is my activation, is equal to x if my x is greater than or equal to 0, 0 if x is less than 0. So this is the most commonly activation function which is getting used in today's architectures, as it's means it is faster, much more faster than to compute at sigmoid at each and every point the differentiation and substituting the value. So from the computational point of view, it's very easy. So H1 is just a matrix multiplication of X with W1. There's certain bias. H2 is nonlinearity. W2 H1 plus bias. Y is again just a matrix multiplication. It can be, you don't need to add explicitly the bias. Okay, it's W3 H2 plus certain bias. So the whole neural network, what I showed here, It's mathematically presented using this sets of equation. Okay. So I hope this is clear. This is called hidden layers, this H1 and H2. So as I mentioned, it's a matrix multiplication. What the matrix multiplication can do is it can enlarge a vector. It can decrease the size of means norm. I'm talking about a norm. Okay. The size of a vector. It can rotate a vector. It can project to a higher dimension. It can project to a lower dimension. Okay. So with the sequence of this operation, a neural network is a universal approximator for any wide layers of arguments neurons. And this each hidden quantity, which were means number of neurons in the hidden layer, just neuron means you can have an arbitrary number of neurons. It is not something there is a golden rule that you should have this many or that many. Okay, so you can play with any number of neurons in between. But the thing is, you should make sure that the final layer should be of the same dimension as what you want as an output. Is it clear? Okay. So this whole W1 X plus B1 in the content, it was denoted by A1. This was denoted by A2. So I hope I'm trying to use same notation as what was followed during the lecture so that you don't miss out anything. Okay. So basically, we are given certain input. Okay. We are performing a sequence of operation which consists of two parts. The first part is matrix multiplication. Okay. Input means our input is getting multiplied by the matrix. Then we are adding a bias to it. Then applying the nonlinearity, which induce a nonlinearity. Otherwise, see, why we need a nonlinearity? Let me give you an example for that as well. Suppose if we don't have a nonlinearity, then why we need nonlinearity, nonlinear activation basically. Okay, if my H1 is just weight 1, X plus B1, and H2 will be then W2 H1 plus B2, which can be further simplified as W2 W1 X plus B1 plus B2, which is again W2 W1 X plus W2 B1 plus B2. But again, this W2 W1 can be represented as a bigger matrix because these two weights are the learnable parameter in the neural networks. So again, this is Wx plus B format. This whole time is my B and this whole time is my W. Okay, it does not matter how much sequence of operation you do. In the end, if we started having a one layer or having an infinite number of this without activation, both are equivalent. I hope you are getting it. Okay. So that's why you need a non-linearity. Okay. The simple thing for the non-linearity is that a function should not satisfy this. Basically, a linear function satisfies this property. Okay. That is a function is there. X and Y are the 2 points inside a domain of this function. Alpha and beta are some certain constants, scalar constants. So f of alpha x plus beta y is equal to alpha f of x plus beta f of y. Okay, this is what a linear function is. Okay, but in the neural network, we don't want this quantity to satisfy. Okay, we don't want it. Otherwise, it will approximate only the linear approximation, not a non-linearity, because we want basically to approximate any kind of function, any. Okay. So there were a lot of activation, I guess it was discussed. Okay. The first activation was 10h, which is just applying a 10h function. Okay, so 10h is basically e to the power x minus e to the power minus x divided by e to the power x plus e to the power minus x. Okay, then it can be a sigma softmax. So softmax is just one more. We are having an activation which is softmax. So what is softmax basically? So softmax is just, for example, we are having a vector x1, x2 till xn. Okay. Now this quantity, each of the quantity can be from minus infinity to infinity. That is xi belongs to minus infinity to infinity. But the thing is, for example, you are doing a classification task where the output is basically we want in the form of distribution. What is a distribution? So in classification, suppose we have a zero class and one class. So we can interpret it as a distribution that what's the probability of having it as one, and what is the probability of having a certain images as zero. It is a very much crucial in the medical thing. Okay, medical industry basically. So whenever a patient come, a doctor will be having a features. Okay, and he need to specify a drug basically, and any drug depends upon the person. A doctor just cannot say that he will be 100% will be fine after taking a drug. He can give a probability that 90%, 95% based on past records. Okay, so that's why we need to interpret all of the output neuron as a probability. Okay, it's a discrete probability distribution over the classes where each value should be between 0 to 1, and the sum of all the probabilities across the classes should be 1. So suppose the probability of 0 was P0 and probability of 1 is P1. So P0 should be between 1 and 0. Similarly, P1 should be between 1 and 0. And P0 plus P1 should be equal to 1. So this was for the two class. If we have n classes, the same thing. All the n probabilities between 0 to 1. And sum of all the probabilities should be sum of to 1. Okay. So now I hope this is clear that what is feedforward neural network, what is softmax, okay, and what is happening basically. Okay. Now this whole model, as you know that we want to run the parameter W1, W2, B1, B2, this all thing. So last time we did a gradient descent for the parameters. Okay. So what is a gradient descent? So gradient descent is a way to adjust the parameters based on the gradient, that how it is affecting the output. Okay. So we need to optimize the parameter. So if my neural network parameters are theta, I need to find theta star for which my loss is something which gives signal to the model, which model understand. For example, least squared error. Okay. So during regression task, the prediction and the original truth value. We want to make it as close as to possible. Okay. Our loss function should be giving some signal so that we can take a gradient with respect to that and we can adjust the weight. Okay. So the loss will be certain form. Okay. We want to minimize it. So the minimum value of this loss with respect to theta, the parameter which we obtained is I'm calling as theta star. Okay, I need to learn the theta star. So the basic to the gradient descent, we perform a sequence of operations. Okay, to adjust the weights. That is theta t plus 1 is equal to theta t minus eta grad L with respect to theta at theta t, where my eta is the landing rate, L is the loss. I am taking a derivative with respect to theta, which is a parameter of a neural network. Okay. So this is a number. This is the iteration which I will be repeating again and again and again until my means convergence is satisfied. That is, this gradient either become a zero or the gradient become less than certain epsilon value. Okay. So the loss function, we can have a simple loss function which was discussed in the week is mean squared error. That is y minus y cap whole square. So yi summation across I from 1 to n. So 1 by n, you can have an average. This is a loss function we want to minimize in the case of regression. Okay. And the thing is about feed-forward neural network is, for example, if you are from the coding perspective, I'm telling you, okay, so PyTorch, TensorFlow, MXNet, okay, they already have been implemented for you. They compute the computational graph in the backend with respect to all the variables. So I will be giving you the intuition, okay, that what is this, what I say, I mean, what is how the backpropagation happens. So let's take a break of 2 minutes. Okay. Okay, guys. So welcome back again. So because my pencil means for this iPad was very low, so that's why I guess I took up 2 minutes break. So the gradient descent update, I guess it was clear from the last week. So I will be just telling you that how this backpropagation happens. Okay. So basically the thing is we'll be doing for the simple case. Okay. Otherwise it will look means people get scared at the first time that means looking at this whole set of weights. Okay. So the problem is basically, means it's very easy, but kind of a chain rule again and again you need to use. So as I mentioned, the chain rule. So what is chain rule? Okay, just I guess my pencil that we charge for 1 2 minutes. So until then, I will be speaking it up. Okay. So the chain rule is basically that I have a sequence of function. That is a one sequence that is f g of x is there. G of x is one function which is internal function of f. Okay. So the thing is, whenever you take a differentiation of f g of x, then you do it like this: f dash, that is a differentiation with f dash g of x multiplied by g dash of x. Okay, so that is what it's gonna be using it. Okay, so and that was the first thing. The second thing is about the softmax. As I mentioned, we want to interpret the output as a probability distribution. Okay, and all the numbers which have been given. So I don't know what is happening. Sorry guys, just 1 minute here. So in the chain rule, if I have a function h, which is f g of x, okay, then h dh by dx is just equivalent to f prime g of x multiplied by g dash of x. So this is what a chain rule. As our output is just a sequence of weight multiplication, adding a bias nonlinearity. This is, you can think it of as one function. We have a sequence of functions basically. So backpropagation in the sense we are gonna update the weights moving backward along the network. Okay. So before that, let's discuss about, as I mentioned, for the classification problem. We want probability distribution basically. Okay. So with the probability distribution for the over the classes, as I mentioned, it should be positive between 0 to 1, and the sum across all of them should be 1. This is what a normal probability is. Okay. Now, as we are not applying an activation in the last layer, my output will be y1, y2 over the classes. Y I denotes the ith class. Y number of classes is the bn. Okay. All my yi will be some numbers. Let's assume by minus infinity to infinity, basically, but it won't be infinity. Okay. So the thing is, between we want it to convert into a probability distribution. How can we do that? We need to make sure that all our yi is between 1 and 0, and summation over I equal to 1 to n number of classes of yi should be 1. We want to manipulate this vector so that we can able to construct a new vector which we can interpret as a probability distribution. So one simple one way is softmax. So basically what we do is we make a new vector zi, which is e to the power yi divided by summation e to the power yi, where I ranges from 1 to n. So basically, e to the power x, so any function is looks like something like this. Okay, and it's always positive. That's one thing. So we made sure the first condition it's always positive. The second condition we want to make sure that it should be between 0 to 1 and the summation should be 1. So that's why we took means each vector we raised to the power e to the power yi, each element wise. Then we are dividing it by this across all the different distribution we can have elements in that distribution over the classes. Okay, so this is what is known as softmax. So the thing is, this is not only the one class of function which you can construct. We can have a lot different function as well until unless you are satisfying these two problems. These two means properties. Okay. That and the thing is, whenever we have a two vectors, means two distribution of vectors. Okay, that is y and y cap, which belongs to Rn, where n is my number of classes. Number of classes. Okay, so normally we, for example, as I mentioned, for the classification task. This is particularly for classification task. Classification task. Okay. So in the classification task, what we are doing basically, we are want to assign a class to an object with a maximum probability. Okay. But the thing is, we can work with the RMSE loss, which is I from 1 to n number of classes. Okay. Yi minus y cap I square. But there is a catch. This RMSE loss, which we will use, means which is generally used for any regression task. For the classification task, do we really need this thing? The question is that. Because the thing is, suppose my original is the cat and dog classification, two classes. I know absolutely that my vector looks like 1, 0 because it's 100% a cat. And my prediction is certain like this 0.8.2. Okay. But the thing is, using this RMSC, what I'm trying to minimize is the difference between these two, 1, 0.8. So it will be summation, means summation you don't need because two classes are there, just we can write it or expand. So it's just 1 minus 0.8 whole square plus 0 minus 0.2 whole square. So basically we want to increase this 0.8 number because whenever we are increasing a 0.8, 0.2 is automatically getting adjusted by default. That's the point number one. Okay. The second term is basically this gradient. We don't want. See, it's as simple as it is. I just want my model to predict one. Okay. If it's predicting zero, some certain with certain probability, okay, I don't care until unless my highest probability is 0.8, and that I want to maximize as much as possible. So I want to make this as much as closer, this error. It does not matter to me this second term. Okay. So to counter for that, we have a loss which is called loss entropy. So what this loss entropy is? It's just a loss which take y cap and its summation I from 1 to n yi log yi cap. So log function looks something like this. Okay. If you and minus basically. So minus of log will be looking something like this. Okay. And each yi is between 0 to 1. So we'll be having here till. Okay. And the second thing is it's always this log yi is always positive. Okay. And whenever yi is 1, it will be calculating the gradient with respect to the same prediction basically. Okay. So I hope it's clear. So the example which we had in that the loss will be basically log minus log 0.8. Okay. Because the other term is plus 0 times something was there. So, okay, okay, wrong 0.2. So whatever we wanted, we were able to satisfy that. Okay. So that's the thing, I guess. Now let's move on learning the simple gradient descent. Okay. Means that back propagation. So here I will be taking one small example only. Okay. Not very much complicated because it can means whatever you're performing for a 1D type of input, it is equally valid for multiple input. Okay, but the thing is it gets over some process, heavy process kind of. I guess, and that will be, I guess, done in that was done in the lectures. So you can again watch the lectures. That will be better. I am trying to revise the concept so that it's easier to solve the quiz problems because I don't want to assume that you already know this or already know that. And if you haven't watched the lecture, please follow the lecture series. Okay. So we have a x1. So x1. We have a weight. We are getting a11 after applying activation h1. I'm simplifying it basically. A1, h1. Again weight 2. For simplicity bias, we can remove it. Otherwise, the process will be remaining the same. Again, we have a two thing. A2, h2. Okay. And again, the last thing we have y paired here. So it's A3. And after that, we are applying a certain that thing. Activation means for the classification, it can be sigmoid. And for the regression, you don't need to apply the activation. Okay. So basically, my loss, which is a function of theta. Loss is a function of theta because loss it takes y hat and try to give you the loss corresponding to that. Okay. So in this case, we have a W1, W2, W3. Okay, so loss will be certain, it will be certain form will be there. Okay, so that's I'm not assuming, it depends on. So suppose I want to take a gradient of this thing with respect to W1, what it will be. So firstly, my loss I'll be taking with respect to y hat multiplied by y dou of y hat with the activation A3. Okay, then A3 with respect to H2. Okay, then dou of H2 with respect to dou of A2 multiplied by dou of A2 with respect to dou of H1 because A2 is a function of H1. Okay, dou of H1 with respect dou of H1 with respect to dou of A1. Okay, and finally dou of A1 with respect to dou of W1. Okay, so this is how it will be gonna be proceeding it. Okay, so it's just about the chain rule. Okay, so I guess this is how means basically we be calculating the gradient backward. Okay, now basically you know that A1 is just W1 X1. So dou of A1 with respect to dou of W1 is just X1. Okay, so we got this term. Dou of H1 by A1. So it depends upon the activation. So H1 is just sigma A1. Okay, dou of H1 divided by dou of A1 is equal to dou prime A1, comma 1. Okay, so it's very easy actually. You know the individual function very much familiar with that. Okay, but the only thing which get cumbersome is when you add more neurons. Okay, so it's not a hard task, but initially it looks like a very big deal. But with time, it's kind of a pretty much straightforward. And also, no one is gonna ask you. You should just know that how to do it. This means backpropagation. But literally, it means you won't be getting any problem manually to calculate the gradient thing. Okay, if you get it, then also it's easy. It's not something which is hi-fi stuff. Okay, so for example, as one more thing was which was there is I guess I completed the chain. Okay, and the loss function. Let's take a differentiation of the loss function in the C. So you know about sigmoid neuron. So sigmoid neuron, the activation ZZ is equal to 1 divided by 1 plus e to the power minus z. Okay. Now I want to take a gradient of it. So basically the gradient we want to find G dash Z. Okay. So firstly, what we need to do is keeping this thing means firstly we need to do the numerator and denominator thing. So first of all, if we have a form of h by g, then what we does is basically g h dash minus h g dash divided by g square. So I guess this news you might have seen in class 12th NCERT. Okay. So the same thing we are going to be applying it. Here our h is 1. With respect to z is 0. So the minus 1 term will be coming basically. And h is just 1. G prime, we need to find a gradient with respect to divided by 1 plus e to the power minus z whole square. And the gradient with 1 plus e to the power minus z with respect to z is just simply minus 1 e to the power minus z. So overall, if you do, it's just simply e to the power minus z divided by 1 plus e to the power minus z whole square. Okay. The thing is, now you can add plus 1 minus 1 and you can just simplify it further. So that is left as an exercise for you. Okay. So I hope this is also clear. So I guess we can move on solving the problems now. So last year quiz problem we are gonna solving. Okay. So the first thing is the first question is means what is true about backpropagation? Okay. So they have given four options. It is used to optimize the weights in a neural network. It is used to compute the output of a neural network. It is used to initialize the weight in a neural network. It is used to regularize the weight in the neural network. It is as simple as it is. Backpropagation, whenever it comes, it's used to update the weights of neural network. Okay. Now the same thing. Let's look for the second point. Second question. Okay, the first question was pretty much straightforward. Okay. Let y be the two class label and p be the predicted probability of two class label in a binary classification. So it's a binary classification. Binary classification means my output is either 0 or 1, either true or false. It can't be both of them. Okay, and no other classes. That's it. So y is a true label and p is the predicted probability of true label. Okay. So which of the following is the correct formula for binary cross entropy? So as I mentioned, cross entropy looks like I from 1 to n number of classes yi log p means log yi cap. Yi cap is the probability basically. Okay. So this you already know. Okay. Here we are having a two class. So if y, so I have a two classes. Okay. So if probability, let it be, means y is the true label, which either can be 0 or 1. Okay. And p is the probability of true label. Okay. Then the probability of another class. If y is the true class, true label, its probability is p. Okay. 1 minus p, 1 minus y is a false class because we are having a two class, either 0 or 1. If my two class is 0, the other class will be 1. If either my two class is 1, other class is 0. Its probability is 1 minus p. This two sum of 2 1. Okay. So binary cross entropy we want to calculate, it's just simply y log p plus 1 minus y log 1 minus p. So this is my loss function. Okay. And there is a minus sign. I forgot. Okay. So the option is B. Okay. Now let's move on to third question. Okay. Let yi be the truth class label of the ith instant. Pi be the predicted probability of the true in the multi-class. So it's a multi-class classification. Okay. It's given as yi means ith is my correct class, which is yi. And its probability of means the prediction is pi. Okay. And they have asked us that what write down the formula for multi-class cross entropy. Okay. So total there are m classes. Okay. So there are total m classes are given. Yi is the correct instant. It can be anything. And pi is its probability of being correct. So simply if you see our correct probability of multi-classes, just it will be only one term. Just other term will be 0 because it can belong only to one class. So yi it will be 1 in the m class, and just for other classes it will be 0. Okay. And pi is the probability of that class. So ideally the cross entropy loss is just yi log pi. Okay. But the thing is yi is unknown. We don't know. It's given as it's a two label of ith instance. Okay. For the ith instant. Okay. Pi is the in the yi is the two class of the ith instant, and pi is the okay. We have a ith instant. Okay. So we have a different sets of that dampers. Okay. And this ith instant is having a yi as its probability, means it's two class basically, and pi it's predicted. So basically, if you see, if we have a m instance, then it's just basically yi. Then we have number of classes are total. It is yi. Okay. And total number of classes are total number of classes are basically what ith instant basically. So like the multi we want with respect to one instance. So total there, if there are total m classes, then it's yi for the ith instant its class log of PIC. So this is my answer basically. So what does it mean? I have a m classes. Okay. Yi is just denoting me the correct index. Yic what's the correct class. So it will be either one for one of them. For all other classes, it will be zeros. And PUI is denoting its correct probability. Okay. So I guess three questions we are done. Okay. Now cross entropy loss can be negative between two probability distribution. Okay. So it's of the form this thing I from 1 to n, yi log pi. Okay. Okay. And it's the minus sign. So this is what my cross entropy is. Okay. Now the thing is my pi, it's always between 1 to 0. Okay. So log of between 1 to 0, the curve looks something like this. It's always negative. Okay. And yi is always, it's either 0 or 1. It can't be negative. Okay. And the thing is, we are having n classes. Yi is either 1 or 0. Okay. And this pi is between 0 and 1, which is always negative. And we have a whole negative. So negative of negative is positive. So this whole term is a summation of positive, which is always greater than or equal to 0. So it can't be a negative. So the distribution, cross entropy is just means distance between two discrete distribution. Okay. So it needs to be positive. Okay. It can't be a negative. So the answer is no. Cross entropy cannot be negative. Okay. Now the next question, let's solve it. If P and Q are two probability distribution, under what condition will the cross entropy between P and Q be minimized? Okay. So basically the cross entropy between the two distribution P and Q. Okay. So P and Q are the two distribution. We want under what cross entropy is basically P means P log Q. Okay. Means here you can assume it to be means what I say. Huh. P and Q are the two distribution basically, which is given to us. And cross entropy is basically P will be a vector because it will be across the classes. Q will be also distribution across the classes. Okay. So basically, in the simple form, it's all means each and every time will be form P log Q. Okay. And it's summation of each and every individual thing. For example, P is of 5 classes, Q is of 5 classes. Then we can it's each term is means P first term log of Q first term. So like that we have a bunch of numbers. Okay. But each term it looks like P log Q only. This is the function basically. Okay, it depends upon P and a Q. So basically this whole function summation will be getting decreased when each of its term is minimized. So if we can able to find a minimum of this thing, P log Q. Okay. Then whole summation term will be getting minimized. Okay. So how it can be done, basically, that's the question. So P is already given. Just assume P is given. Okay. P is given. And Q, you just, this is a function, take a derivative with respect to Q. So it will be P by Q. Okay. Now again Q, just assume it to be, Q is given. Then the P will be take a differentiation with respect to P, it will be log Q. Okay. Now the thing is basically to minimize each of this term. Basically each log Q should be equal to log P by Q. Okay. What will be the value of P and Q so that this equality is satisfied? So basically if I take P equal to Q, okay, if my P is equal to Q, then this whole equality is getting satisfied. Okay, so log is there. The log basically at what point it will be getting P and Q are just ratio basically. And if you take P equal to Q, okay, then it's giving us log Q, which is 1. Q is just E, means here 2 to the power 1, 2. E basically. It's a natural log. Okay. So this is the means basically each and every term should be equal. Okay. That's where the each thing will be 0. Okay. So that satisfies means see that cost entropy is minimized. So if my P belongs to a vector Rn, Q belongs to a vector Rn. Okay, so what I meant is basically the cross entropy loss is just summation of Pi log Qi. Okay, so as it's a summation from I equal to 1 to n. Okay, if we want to minimize this loss, then we need to minimize each and every term. Okay, what's the minimum value this or it can take? Log is there. We know that this is a minus sign. Okay, so minus of log function. So log looks something like this. Minus of log looks something like this. Okay. Suppose Pi is given. Sorry, this. Okay. So this is what means this log Qi will be looking like. Okay. And the thing about Qi is that it will be between 0 to 1. Okay, something here. So it will be certain value. And Pi is already been given, suppose. Okay. So basically, the thing is, we want to minimize it over each term by term. If my two terms are there, Pi and Qi, okay, I want to minimize log Qi. What's the minimum value log can take? It's x into log x. Okay. So basically, you can think it of as it's just x log x. We want to find the minimum value it can take. And it's only possible when both of my terms are equal. That is pi is equal to qi. So the correct answer is p equal to q. So, but how to justify it basically? Okay, we got it mathematically that what is happening means intuitively. Okay, so basic thing is we want to bound this term pi log qi. Okay, and log minus of log qi is from 0 to infinity any term. We are multiplying by it pi. So log qi is between minus infinity to 0. Okay, and pi we know about that is between minus log pi. Okay, 1 and 0. Okay, so the thing is basically that we want to take derivative of this thing with respect to each individual term, means with respect to pi, with respect to qi. So with respect to pi, it's log qi, and with respect to qi, it's just equal to pi by qi. Okay, so this is the term we are going to be getting it, the whole differentiation. It's a directional derivative kind of concept. Okay, we want to make it both equal. When this will be happening? If all my pi and qi terms are constant, means becoming equal, so that this log qi in that case, if it's 1, log some value is getting 1. Okay, so if log x is equal to 1, okay, here the base is 2 to the power 1. So basically so so basically the thing is each under the condition that pi equal to qi, this two probability distribution will get minimum. Okay, so let's move on to next question. Okay, so the next question is which of the following is false about cross entropy loss between two probability distribution? It's always in the range 0 to 1. False. We need to find false. Okay. Cross entropy is just the same thing which I'm writing again and again. Yi log yi cap. It's a minus I from 1 to n. Log yi as its range is from 0 to infinity, and yi it can be between 0 to 1. Okay. The first option is it's always between 0 range 0 to 1. It's false because the second term can be between more than that. Okay, it can be negative. It's false. It's always positive, as we have already shown. Okay, it is always positive. That's true. It can be 1. That's also true. It can be 1 only when can it be 1 probability? It can be 1. Okay, so yi is So this is a cross entropy, and they have told that the minimum value it can be one. So yes, it can take a value because the range is between 0 to infinity. So it can be one. Okay. But in which case it can be one, basically. That's the thing we want. Okay. So it can be one when each, the simplest case will be taking all of the terms is 1 by n. When y is 1 by n. Okay. And ei is just e. Okay. ei. Okay. Yi you can take 1 by n. Okay. And yi cap. Yi cap, it's a log. E is the base, suppose. Okay. Then yi cap is e as well. Suppose we could take it as e1 by e1 by e. Okay. So let me just check it quickly. Okay. Yeah. So the correct answer is it's always between range means which of the following condition is false. Okay. So it's in the range 0 to 1 and it cannot be negative. These two conditions are false. So the thing is it can be one. Yes, it can be one because this whole term is between 0 to infinity. So when it is one, finding that is kind of a means, means kind of a task which will take some work. But if you want, the simple thing is suppose my yi equal to 1. Okay, my yi you can take yi. It is of the vector 0, 0, 0, 1 something. At one class it will belong. So that is 1. Okay. We want this log yi cap. Okay. Yi cap is the probability minus of yi cap. So log 1 by yi of cap. Okay. Yeah. So this yi cap, you can take it as of what I say 1 by e. Okay. That's a valid thing. 1 by e. Okay. It's less than 1. And in that case, it's equal to 1. Okay. So there are a lot of different instances where it can be 1 as well, but I took a simple case. Take a ith class, it belongs to 1, rest of the class is 0, and yi cap is 1 by e. So log 1 by e is negative, negative, negative will become positive, and log e is just 1. So that can be 1. The seventh question. The probability of all the events x1 till xn in a system is equal. Okay. So we have n classes, suppose all the classes are equal. What can you say about the entropy of a system? Okay. So basically, first of all, entropy is given as summation over all the event minus p of I log p of I. So this is the entropy formula. Okay. We have given that x1 till xn. It can be of this event. Okay. And each of them have a equal probability. That is 1 by n. Okay. So if you calculate this thing, it's minus 1 by n. Okay, summation I from 1 to n. log 1 by n. Okay. So the thing is, all the terms are equal, and then will get cancelled. So minus of minus, it's log n. Okay. And log n is always greater than 1. Why? Because n is, if my event is 1, okay, then log 1 is basically 0. Okay, but my n is 2. Think it of this. This is my function. For 1, it's 0. So, but my probability will be at least 2. Means the number of events will be at least 2. In that case, it will be always greater than or equal to 1. So the answer is the entropy h of x in this case will be greater than or equal to 1. Suppose we have a problem where x and y is related as something. So next question. We have been given y is equal to x to the power 4 plus 1. Okay. Which of the following is not a good choice of activation in the hidden layer if the activation function at the output layer is linear? Okay. So the thing is, we have we have an input. We have numbers hidden layers. We need an output, and the output, the activation is just linear. They are asking that which of the activation function we cannot use in the hidden layer. The option is A, linear, B, that is Redu, C, sigmoid, D, 10 actions, 10 inverse of X. The thing is, the means activation at the last layer is linear. If you are using a linear activation in between the hidden layer, as I mentioned previously, that W1, this thing, W1X plus B1, we are applying activation here. If it's a linear activation, whole formulation is just a linear. So it can't be this. It can be any one of this, which is adding a non-linearity. So the answer is A. Okay. We have a ninth question. We are given a probability of event A. We have a two event A and B. Okay. So A is having a occurring of probability of occurrence is 0.95 and B is having 0.05. Which of the following statement is true? Event A has a higher information content. Event B has a low information content. Event A has a low information content. Event B has a high information content. So the thing is, information can be, means you can interpret it as the entropy, the randomness. Okay. In the first case, we have a 0.95. Okay. So suppose if you just calculate the entropy with the each individual term. Okay. So for example, 0.95 multiplied by the log 0.95. It's just minus of 0.95 log 0.95, which is 0.0211. Okay. Now, suppose if we take 0.05 multiplied by log 0.05. So minus 0.05 log 0.05, which is 0.06. Okay, 5. So the information content in A is this, information content in B is this. That is simply probability of that event, negative of probability of that event, log of probability of that event. So in the first case, it's 0.02, the amount of information, because we are much more sure about that occurrence of the event. Lesser the probability, more the kind of randomness, and more the information we are having. So that's all. So the correct answer is B is having a high information content, A is having a low information content. Okay. Now the last question, 10th. Which of the following activation functions can only give positive output greater than 0? Sigmoid. Sigmoid was between 0 to 1 as it's bounded. 0 is also from 0 more than means it always give a positive. 10H, it's from -1 to 1. And a linear is just minus infinity to infinity. And the question is greater than 0. So sigmoid. Sigmoid achieves a 0 at an infinity. So sigmoid we are having of the form as greater than 0. 0 is takes the value 0. 10H is negative, -1 to 1. Linear is minus infinity to infinity. So it's 1 divided by 1 plus e to the power minus z. So the limit sigma of z as z tends to infinity, it's 1. Okay. Sorry for this mistake. It's 1 because e to the power minus infinity, e to the power minus infinity is 0. So 1. Limit z tends to minus infinity. Okay. Sigma of z. So e to the power minus infinity, e to the power infinity, 1 divided by 0, 1 divided by infinity is 0. So it achieves the 0 in the limit case. So that's why the answer is A, sigmoid. Okay. So that was the questions for the week 3 last year. So we have solved and we have just also went through some of the examples, means content for this week. So I hope you enjoyed the today's session, guys. So that's all for the today's session. Thank you and have a nice day.